morning, everybody, and welcome to today's talks. Before I introduce the speaker, I'd like to particularly welcome Krishnendu, because it's so good to see him. I don't want to make him too jealous by saying what a wonderful time this conference he's helped to organize has been, but it's really good that he's finally been able to make it, so welcome to you. So our first speaker today is Sara Maloni from Virginia, and she's going to be talking about geometric structures and fiber bundles associated to Anosov representations.
Thanks, John, and thanks the organizer for this really wonderful conference. It's really nice to see so many friends I haven't seen in a long time. So today it will be a lot of background. I'll start really with going through geometric structures to motivate the question that we will discuss. We'll start in the classical case of Teichmüller theory, quasi-Fuchsian setting, and then we will try to discuss higher Teichmüller theory. And since that area, the definition comes from representation, we will then try to see how much we can go back. It's like, are there geometric structure associated, and what can we say about their topology? So hopefully I will arrive at the end today to say something about the joint work with Daniele Alessandrini, Nicola Tolosane, and Hannah Winard. And tomorrow we will discuss, so in particular, I gave it away, so these quotients will be fiber bundle. Tomorrow we will discuss, hopefully, the topology of the fiber. Please stop me at any time. And if time, I have a lot of proofs that we can do together. I might skip depending on time. Actually, I was supposed to start this. Yeah. Okay, so today we will be in the setting of a closed orientable surface of genus 2, and we will put an hyperbolic structure on it. And Teichmüller space is the moduli space of such structure, so marked hyperbolic structure up to equivalence, and which we can identify with the Fuchsian representation, so representation from the fundamental group of a surface into the isometry of H2 that are injective and such that the image is discrete up to conjugation. And so in higher Teichmüller theory, like we really use much more this second definition. And so what we are going to do is that we are trying to replace the target group with other group of higher rank, like PSL, DR. We will see we will define those spaces and trying to see how much we can go back. And so, so this is the plan. So we will really start with geometric structure, Teichmüller space, and quasi-Fuchsian space. Then we will discuss higher Teichmüller setting and Anosov representation. That will really be the framework that I will discuss more. So we will, you should think more of the setting of quasi-Fuchsian representation rather than Teichmüller space. And then we will discuss geometric structure associated. Okay, so geometry, like we'll use the Klein definition of geometry. So for us, a geometry will be always a pair, Gx, where X, the model manifold, like a connected homogeneous manifold, and G, a Lie group that acts transitively on it. Like these are some of the spaces. The geometric structure that we will see today will be G over quotient of G, so G mod some parabolic. That will be, they will come as a generalization of this complex projective structure that is the boundary of hyperbolic space. And so what does it mean to put a geometric structure on a manifold? Geometric structure on a manifold is the data of an open covering. In this case, like the picture is of a surface. And you have charts. So for every open set, you want to map into your model space. what you want is that for every connected component of the intersection of two charges, you want to find an element of the group that make you translate from one chart into the other. So this is the local definition of geometric structure. We will see soon the more global definition, or at least a part of it. But which question can you ask about geometric structure? I think like you might be handle a manifold and the geometry, and so you might ask, can you put this geometry on this given manifold? And in the cases where the answer is yes, you can ask in how many ways can you do it. In some cases, you can do just in one way, so this will be a more phenomenal or rigidity. In some cases, you can do in multiple ways. So like you see this flexibility that will be the framework of today. So this is Heresman started discussing this question, and Thurston really brought the subject again back to life. With respect to the first question, again, there are many directions that we can go, but maybe one easy example is the geometrization of closed surfaces, where we can see that on the sphere, we have the spherical geometry, on the torus, the Euclidean geometry, and then on all the other surfaces that we will care about today, you can always put a hyperbolic geometry. These are all metric geometry, but in general, like the geometry can be different. These are all G is always the isometry of these spaces. And this is what we were saying. So with respect to the second question, like you have some flexibility phenomena and you have some rigidity phenomena. So today we will be in this part of the talk. We will really study moduli space of geometric structure, or moduli spaces that we will see then in terms of geometric structure. Any question? Okay, so like this is what we mentioned before, is that Teichmüller space defined as a Mark hyperbolic structure really correspond to Fuchsian representation, so discrete and faithful representation. And how to do that? So the way that you construct this homomorphism from the definition that we gave before is you cover your loop with charts, nice charts, and then you reconstruct the path back in your space X. So you have the first chart and you have the second, and you map it back. And so like this holonomy like tells you the relation between one chart and its image. And so the element that you associate in G, in PSL2R, is really the element that connect these two endpoints. And like these are just two pictures that we have today from Émilie Dumas that are of this discrete, like I think this picture really like give an idea of this sense of discreteness. And so I forgot, I think one is PSL2Z, and the dot is really thinking of PSL2R as unit tangent bundle of H2. And so the dots is the length of these vectors. So yeah, Émilie has a really wonderful picture. There will be another soon about this higher Teichmüller setting. And in fact, you can even, for this picture, you can even go and play and move them around. Okay, so quasi-Fuchsian space, like again, we discussed it in many talks before. So let me just recall briefly. So like one way to motivate quasi-Fuchsian space is just to see how Fuchsian group acts on H3. So if you take a Fuchsian representation in PSL2R, so we have seen that this discrete group X on H2, and the quotient is the manifold. When you look at this action on H3, then what's happening is that you have a copy of H2 inside H3 that is preserved, and in fact, all the equidistant plane get preserved under this action. And so when you take the quotient of H3 under a Fuchsian representation, what you see is that at each level, you see your surface, and so you get a 3 manifold that is homeomorphic to S times R. And the point of quasi-Fuchsian, the definition of quasi-Fuchsian representation is really how much can you deform this representation by keeping the geometry the same. And so you can deform with this quasi-conformal deformation, and still the picture that I draw is going to look similar. So like I think yesterday you have seen a slightly different definition. The way I define quasi-Fuchsian representation today is discrete representation now in PSL2C, so isometry of H3, such that this limit set is a Jordan curve. And so the limit set is this, like I think Jean-Marc drew it yesterday, like you take any point in H3 or in CP1 and you look at its accumulation, and so it's a set of accumulation point of any orbit. Okay, so associated to this quasi-Fuchsian representation, there are two, probably more, but two geometric structures that we'll consider today. So one is the hyperbolic structure of the 3 manifold that you obtain by taking the quotient of H3. And then we have the structure at infinity that came up in the Burse embedding that Jean-Marc introduced. Is like the point is that the complement of the limit set, this domain of discontinuity, are these disjoint union of these two topological disks, and they have a complex projective structure. So a structure that is Gx, where G is PSL2C and X is CP1. This second point of view will be the point of view that we will generalize today in the higher Teichmüller setting. So when we will look at representation not in PSL2C anymore, but in some other higher rank complex group. And in fact, these examples are really prototypical example of both like general hyperbolic 3 manifold, because this quasi-Fuchsian representation comes in the end of hyperbolic 3 manifold, but also of convex compact representation. So maybe people that are more interested in geometric group theory. And if we want to think in fancier term, like we can write H3 as the Riemannian symmetric space of PSL2C, and the CP1 as is Furstenberg boundary. Like we will see these flag varieties appearing in the boundary of the symmetric space, and these will be the space that we will say something about, with the hope that maybe understanding what happened at infinity or what happened in the boundary will help us say something about what's happening in the symmetric space. The work in the symmetric space, I think, is harder because when you go to higher rank, you have flats, and so things don't work always so nicely. Any question? So, okay, let's move to the higher Teichmüller setting. So I'll start with a little tour of higher Teichmüller spaces, their definition, some properties, but then we will move to Anosov representation. And I think higher Teichmüller spaces have been studied a lot, and they are the higher rank generalization of Teichmüller space. But for us today, we need a weaker property that we will discuss. And so, like, how to define these spaces? One way to define these spaces is as component, full component in the character variety that are all made of discrete representation, such that the target group is higher rank. It's not even obvious that you can find such spaces. So do these spaces exist? And if they do exist, do they have some nice feature like Teichmüller space? In fact, we will see, so very often we frame these in the second setting. We will see today some answer in the opposite, like some feature that do not appear in the classical setting that instead appear here, some differences too. Okay, so can we find such spaces? The answer is yes, and I think like we are almost classifying them all. So the first example was done by Ichin, and I'm not sure we will define it today. So like the Ichin representation, what you can do is that you can define Fuchsian representation by taking PSL2R and embedding with a reducible representation PSL2R in higher rank group. These define Fuchsian representation in this higher rank setting. And then the Ichin component is really the full component that contains Fuchsian representation, like all the formation of this Fuchsian representation. This was not the definition that Ichin gave. So Ichin introduced and studied this representation in a different setting and using Higgs bundle method. And he proved that this component was a ball. And it was the later work of Labourie and Fock-and-Goncharov that using different method, they prove that all these representations are discrete and faithful. Like Labourie using the notion of Anosov representation that we will see today, and Fock-and-Goncharov using the notion of positivity. And in fact, from their work, then you can see also new example of this representation. So one next example is maxima representation. This was done by Burger, Yotzi, Wiener, Burger, Yotzi, Labourie, and Wiener. And like you have restriction on the target group that you need for these different definition. You have positive representation really coming from this work of Fock-and-Goncharov, and then Guichard, Labourie, and Wiener. And then more recently, work started by Guichard and Wiener, then Guichard, Labourie, and Wiener, and also like other work of Collier, Garcia Prada, and lots of their collaborators, where they generalized this notion of positivity to theta positive representation, and they were able to classify and try to count all of these components. In fact, Higgs bundle that we will not discuss today is a very powerful method when you want to count. We will see this picture again. This picture is a picture by Emily Dumas, where, and is based on work of Gisson, Lee, and Stecker, that they look at Anosov representation, and when you have one-dimensional complex setting, and they have a method to say exactly when certain representations are Anosov, and this is the picture. But like this is the picture that we will see soon, but the Ichin picture in this setting is this green line. Yeah, so this is the fundamental group of an orbifold, S2-555. Yeah. Yeah, it's a triangle group to have this one dimension. Yeah. Oh, yeah, I think it's, whoops. Yes. Oh, it's not, yeah, okay. Yeah, tell me if you don't see, because I see differently here. Okay. Okay, so do these spaces have some nice properties, like Teichmüller space? And in a lot of settings, the answer is yes. So in many cases, these components have a trivial topology, like for example, the etching component is a ball of a certain dimension. The mapping class group acts properly discontinuously on them. You have some mapping class group invariant metrics, so we discuss a lot of metrics in the setting of Teichmüller space, and so here there are a lot of, there has been a lot of discussion. Some metric in some setting like SL3, and some metrics maybe more general like the pressure metric. And then you can think about compactifying this component in the same way that Thurston compactification work. There are various ways to define Thurston compactification using real tree, using lamination, and there are a lot of these compactification that work. Another setting is the color lemma. So in this component, the color lemma works. So there are a lot of ways in which this component really behave similarly, like Hitchin, like Teichmüller space. But there are also some cases where they behave differently. Two examples really come from maximal, this second definition, this maximal representation in SP4R, for example. So some maximal component have non-trivial topology. So in some cases, the topology is trivial like Teichmüller space. In some cases, not. And there are even components in which you do not have any Fuchsian representation. This is another, so these are called exotic components, and there are many in SP4R and in other higher group. And for example, like one of the theorem, like the theorem that with my collaborator that I will discuss today, will not tell you anything about this component, because in our setting, we will need the Fuchsian representation in the component to conclude, okay? Yeah, yeah. No.
No, in the PSL DR case, there's up to conjugation with the What happens with these other groups?
Like the irreducible one is one, but like you will see that you will have for the things that we will discuss later for Anosov, we will use many different embeddings. So we will relax this notion of Fuchsian. So here when I say Fuchsian, I'm not necessarily caring about, like the irreducible, but like for Fuchsian, I just want an embedding. So yeah. And the last question that I will really say nothing, but if you are more interested in more arithmetic question or question coming from number theory, like this setting might be quite interesting because you can see behavior that you do not see in the classical setting. I think these really powerful results of Long-Read and Thistle-White, where in the etching, I think they study SL3R, and they find many pairwise not conjugate integral representation. So because you have more space, so like it's, but yeah, I will say nothing about this, but I just wanted to mention that in some cases, the behavior is not always the same. Yeah. Sorry? So here the question was like, can you, like, is the behavior always the same? And the answer is that in some cases, the behavior is not the same. So because in the SL2R, you do not find non-conjugate integer representation, while in the hitching component, you find many pairwise non-conjugate representation. Yeah, and I think they started, and then Burger, Laborie, and Wiener, they have other work about that. But I will say, this is all I'm going to say about this question. Is really not the direction, but I wanted to put it there as an example, such that sometimes things behave differently. Okay, so on the other hand, I spent all the time before convincing you that, and other people did before me, quasi-Fuchsian representation are really interesting. Well, quasi-Fuchsian representation are not an example of a higher Teichmüller component, because in the same component where you have quasi-Fuchsian representation, you can deform in the same component and arrive to the trivial representation. So very far from being discrete. Okay. So for the talk today, we want to look in this setting. So the notion of Anosov representation is the one that we will care about. And so we will not have a full component of the character variety behaving nicely, but we will have connected components where we have this nice behavior, where we have this Anosov property. And so what is the definition of Anosov? I'm giving here the definition in one particular setting, and I'll tell you in a second in how many ways you can generalize that. But here I'm looking at, for example, representation in PGLDC that are Borel-Anosov. So already here, Borel is a choice of a parabolic. In this setting is the upper triangular matrices, is the minimal parabolic in this group. And also the definition of Anosov has many equivalent characterization, many. So I'm giving you one, but yeah, there are many. One way to define Anosov representation is with the existence of a limit curve, like in the quasi-Fuchsian setting, where we had our limit curve. Also here we have a limit curve that I'll denote Xi from the boundary of the group. The boundary of the fundamental group of S is RP1. In this case, into the full flag of C to the D that we can write as this quotient G mod this Borel group. What do we want from this limit map? We want it to be rho equivariant. We want it to be continuous. We want it to be transverse in the sense that if you take any two distinct points, we have these, we associate two flags, and we want these flags to be transverse. And finally, this third point is the more tricky one, where again, you can define it in various ways, but one way is using this strongly dynamics preserving representation. So for any infinite sequence that tends to gamma plus and gamma minus in the boundary, you have a behavior of the image. So if you look at rho of gamma n applied, I'm not sure what to do about it. Yes, sure. So I think the way so for every gamma n such that gamma n tends to gamma plus and gamma minus, what you have is that rho of gamma n apply to Y. I'll tell you why, where it belongs in a second. What you want is that you want C plus of gamma plus. And so like the Y is not everywhere, but like you need to be transverse, Y transverse. Like in this case, you have, like for example, gamma, this will be C gamma plus, this will be C gamma minus. You want to be transverse to C gamma minus. Yeah, thank you. Okay, so does it make sense? Like is this, so this representation of this north-south dynamics or this convergence behavior that, yeah, that is really crucial. Question? Yeah, oh yeah. So, sorry, the slide before. Why quasi-Fuchsian space is not a Teichmüller. Yeah, so quasi-Fuchsian space, like the way we define higher Teichmüller setting is that you want the whole component to be made of discrete groups. And so for quasi-Fuchsian setting in the component, like in PSL2C, you have two components. And so in the same component that you have quasi-Fuchsian space, you can deform moving continuously until the trivial representation. So you have a lot of representation that are non-discrete. Like quasi-Fuchsian setting, usually we work for quasi-Fuchsian representation, we care about their boundary that are still discrete, but you move outside is very wild territory. And so, but for Anosov representation, we can focus on this nice component of nicely behaved, yeah. Yeah.
Are you allowing, on the representation type preserving, are you allowing gamma plus and gamma minus?
Gamma, no, no. Like,
this is the convergence.
Exactly, yeah.
And, right, so, but there's a sense in which the attractor and color could be the same thing.
Yes, but not here. Like exactly. So there is a lot of work trying to think about geometrically the analog of geometrically finite, where, for example, one way to define it is trying to think about. So here, like here, we all have conical limit point. In this other setting, you allow conical and bounded parabolic, and there are many equivalent definitions. In fact, like with Teddy Weisman, we are now thinking in terms of convergence action or extended convergence action that really capture that behavior. And in fact, they also capture for subgroup of the mapping class group that also like this notion of convesco compact and geometrically finite also have these. Yeah. These no parabolic, yeah, yeah. Other question? And so as I was saying, like you can generalize these many more, like first, the domain doesn't have to be a surface group. In this case, it can be an hyperbolic group. For today, like it will be hyperbolic group. I will just stick to that case, even if our theorem works more generally. The target group, you need a semi-simple Lie group. We'll see some other example, like symplectic group. I think probably that's it, but like there are many that you can think. And here, like the parabolic doesn't have to be the minimal parabolic. It doesn't have to be Borel always. You can have a different parabolic subgroup. So for example, here I could have chosen the stabilizer of a point, the stabilizer of a line. And so in this case, the parabolic would have been a maximal parabolic, would have been much bigger. If I do that, so if instead of having the Borel, I change to another parabolic, I just have my limit map landing in a different space. So if you are in PGL-DC, then these are all partial flags variety. And with different group, you work in maybe isotropic partial flags or other generalization like that. In fact, for in some cases, if you understand the behavior in some case like PGL-DC, then you find a way to understand how to translate in other setting by understanding the right, let's say, Lie theory. But just to connect with higher Teichmüller space before, like all the higher Teichmüller representation that we discussed are Anosov. Yeah. Yeah.
So you're portioning to a smaller space, and you look at the Anosov representations there. Those guys pull back to which ones?
In this case, yes. Well, if you are Anosov with respect to the minimal parabolic, you also have all the limit curve into this. And we will see that for what we will discuss for representation, we will see that it will be important to consider some non-minimal parabolic, and then you see some strange behavior differently from quasi-Fuchsian space, where you might have the limit curve in one space and the domain of discontinuity in another space. So yeah, that is one of the complications that comes up. Yeah. Yeah. Exactly. So yes, you don't have the behavior like in the quasi-Fuchsian setting that the domain of discontinuity, you just remove the limit curve and you win. In this setting, you need to remove more. And so you need to, yeah, exactly. Yeah, I will call the thickening of the limit curve. That is what you need to remove to get this domain of discontinuity. And will also give you a non-uniqueness, because there might not be a unique way to thicken. But yeah. And this is the picture that I promised. Like, I think I have this mistake everywhere. These are this nice picture made by Lee Gisson and Lee and Florian Stecker, where, I really like, because you can see concretely, and it really reminds you of some of the pictures that we have seen, maybe about quasi-Fuchsian space in some cases where you can do those pictures. Okay, so now we are discussing geometric structure associated. So like we define this Anosov representation just from properties of the representation, but are there nice geometric structure associated? And if yes, what can we say about them? And so the answer is yes, and this is really wonderful work of Guichard and Wiener and Kapovich, Lieb and Porti. I think today I will mostly use maybe the point of view of Guichard and Wiener, so I will not talk about balance ideal, but they were the first and defined this domain of discontinuity in many cases. Kapovich, Lieb, and Porti, they have a more maybe they use a different combinatorial way to define when you can define this domain of discontinuity. And so there are a few new cases that they cover. And Dumas and Sanders were among, I think, the first to study some of these Anosov representation where the target group is complex and this domain of discontinuity. And so we are, yeah, we did some work. I'll explain. So this is something I was mentioning just before, like how you should think of this domain of discontinuity for Anosov representation. Unfortunately, the picture or what's happening for quasi-Fuchsian representation can be a little misleading, because in that setting, it's rank 1, so you only have one boundary. You can think in this case, when G is ESL to C, we have the boundary as CP1 that you can think as flags in C2, or even isotropic flag. This is also ESP to C if you want. And so here, what's happening is that removing the limit curve, then these two topological disks are a domain of discontinuity for the action. So in this setting that we will discuss, it will be more complicated because we will have the limit curve possibly in one space, and you need to change flag space to get this domain of discontinuity. You might not do it uniquely, and so it becomes, yeah, you have much more variety for domain of discontinuity. Yeah, so this is what Guichard and Wiener and Kapovic, Lieb and Porti, they did. And one really nice properties that will be crucial for us is that these domain of discontinuity are co-compact, in the sense that if you look at the quotient, is a compact manifold. And this co-compactness will be really crucial for us, because in my work with Alessandrini, Tolosan, and Wiener, what we do is that we study the topology of this quotient in one nice setting, so for Fuchsian representation, and then the co-compactness tells you that the topology is constant on the whole component. And so these domain of discontinuity, or this quotient, they have, by the way that they define, they have a geometric structure. They are GX, where X is this partial flag space. So here I have been general, like I said, you land in some P and you might change in some Q. So there are ways to choose the Q. And one thing that their theory, that it's hard to say in general, is when this domain of discontinuity are non-empty. What Guichard and Wiener prove is that you can always embed this domain of discontinuity in a bigger space, and there you can assure the fact that they are non-empty. But in some cases where this thickening is big enough, maybe you remove everything, and so your domain of discontinuity can be empty.
Suppose you look at the pre-image of that in your full flag.
Yeah.
So then you get a bundle.
Yeah, and in fact, ours, so in many cases, then the topology, if you understand in some setting, then in the other setting, like flag varieties, it will be just a bundle. Yeah. And there is a nice work of Leon Carvajales and Florian Stecker that I will not address today. And what do they do is that they generalize the previous work, and they define this domain of discontinuity on more general homogeneous spaces like pseudo-Riemannian symmetric space. They were inspired really by the domain of discontinuity, the discussion, the mass theory in PSL2R cross PSL2R. But those spaces are in general not co-compact. And as I was saying, for our theory, the co-compactness is really crucial. Okay, so in the remaining space, time, I'm hoping to prove, so give you a construction of this domain of discontinuity, prove that they are domain of discontinuity, and then discuss our results, the fact that these quotients, the topology of this domain of discontinuity, they are always bundled over the surface in this case. In fact, what I might do is that I might skip the first proof that when you remove this thickening, then these are domain of discontinuity, and do it at the end if I have time. Does that sound good? Okay, so yeah, in fact, I'll discuss this construction in one example, because the way that Guichard and Wiener they do is that they construct this domain of discontinuity in some setting, SO PQ or SP, and they discuss how to use this construction and then embed in other groups. But I don't want to really introduce the whole Lie theory that we need for that, so I'll try to hide or the Lie theory so swap under the rug. Hopefully I manage, yeah. Well, there is also that, but in order to, for example, define the domain of discontinuity in SLN, they discuss the construction in these two other groups, SOPQ or SP, and then they discuss how to, they use embedding of those groups into like SLN, and discuss in general like how to define domain of discontinuity in SLN. And so, like you can also just take the definition that comes up after seeing what they are and finding an equivalent characterization. So they embed and then they describe it self-containedly. And so you can also just rerun the machinery that they ran before to see that they are domain of discontinuity. Kapovich-Lieben-Porti theory is in some sense maybe more clean because they use this combinatorial setting, and so they tell you what to do for this balance ideal. But I really like, I don't know, maybe that's the theory I learned it from Anna, and I really like the picture, like you have this curve and you have this thickening that you remove, and yeah. So I'll do it in this one particular case of SP4C, but the construction is very similar. And so in order to discuss this example, we consider C4, the vector space C4, as a homogeneous polynomial in two variables of degree 3. And on this space of polynomial, you can define a symplectic structure that concretely you pair x3 and y3, and then you pair x square y and xy square. Everything else is 0. And then like the symplectic group of C4 with this symplectic structure is really homeomorphic to SP4C. And we will work, we will have two homogeneous spaces that come up in this example. One will be CP3, so the projectivization of C4, which in another way, like all lines are isotropic with respect to these symplectic structures. And so the associated homogeneous space is the whole CP3. And then the other space is isotropic subspace of maximal dimension. These are Lagrangian. And so in this case, they are planes that are equal to their orthogonal with respect to the symplectic structure. And so we will have to go back and forth between CP3 and Lagrangian. And so the Veronese embedding, so we can even describe it very concretely in terms of this polynomial. So I'll discuss, in fact, you have an embedding into the CP3, but also in the Lagrangian. I didn't write it today. It will come up tomorrow. For Fuchsian representation, this limit curve is really given by this Veronese embedding. And the way to do is that you map a point in RP1 into the polynomial that has that point as a triple root. And in fact, by the way that we define, it's clear that you can extend it, in fact, to map from CP1 to CP3. So like how you construct this domain of discontinuity, first you define the bed set. This is the thickening. What you do is that for every point in RP1, you remove K CT. So CT is, this is a line. And so what is K of a line? These are the Lagrangian that contain that line. So what you are doing is that you have this limit curve in CP3, and you remove all the Lagrangian that contain one of these lines. So you remove all Lagrangian that contain a line that is associated to a polynomial with the triple real root for Fuchsian representation. And so the theorem is that the complement of this thickening, yeah. Whoop. No, like, whoop. Yeah, I just wrote that the thicken, like the complement of the thickening is the domain of discontinuity. So omega rho, that you define it in this case as Lagrangian minus this thickening. This is so here maybe we don't even have the representation. Is a like you should think of this as the domain of discontinuity for Fuchsian. And as you have seen, we have a limit curve in CP3 and the domain of discontinuity in Lagrangian space. And so, like, yeah, this works more generally, even when your limit curve is not coming from a Fuchsian representation. It's just in this more general setting, it's harder if I want to give you a closed formula for the limit curve. The same as for quasi-Fuchsian representation. So we have a Anosov representation, in this case with respect to the stabilizer of an isotropic line. And you take the thickening, you remove all Lagrangian that contain these points, and so the complement is a domain of discontinuity, and it's co-compact. Okay, so maybe I'll skip this proof, and I'll discuss our theorem, and if I have time, I'll discuss the theorem. So, like, and the way to prove that, yeah, so maybe I'll just. So the point is that there are some properties that are really coming easily from properties of the limit curve. So the fact that the domain of discontinuity is open and gamma invariant is because the same properties is for the limit curve, and this thickening is a line bundle over this limit curve. And for the proper discontinuity, this is what most of the proof is, and you use contradiction. So like they just use in Guichard and Wiener, they use this equivalence characterization of proper discontinuity. and is the fact that you take two compact in omega, and you look at the set of elements such that gamma of one intersect the other. You want this to be finite. So the point of the proof is really assuming this is infinite. This is one of these sequence gamma n that are divergent, and you really use the properties of this divergent sequence to find the contradiction. With you find points that are both that should be in B and in the complement of B, and you conclude. So yeah, if I have time, I'll go through that. But I wanted to discuss first these, at least the main idea of like our results about these quotient. So like Guichard and Wiener and Kapovich, Lieb and Porti, they give you this domain of discontinuity, and they study the topology in some cases. Emily Dumas and Andy Sanders, they studied this quotient in some other cases, and they conjecture that these are always fiber bundle over the surface. And that's what we prove. What we prove in most cases. So first of all, like these results was known in some cases, like it was known when your domain of discontinuity landed in projective space. In the case of SO2N, like you have this photon space. And so in this case, again, Guichard and Wiener studied the topology, and Collier, Tolosan, and Toulis, they have an alternative proof. And then Dumas and Sanders, they discuss the flag space. And so what we do is that just have a general construction to prove that this manifold, M rho, is always a smooth fiber bundle over the surface. I think I call it S in this slide. And in which cases we can conclude, so we can conclude in all components of Anosov representation that contain some Fuchsian representation. So this is a mild condition because most of these components contain Fuchsian representation, but there are these exotic components where you don't have, like all the representation are Zariski dense, so you don't have any Fuchsian representation. Yeah.
Have you defined omega rho in general?
Yeah, I think I define it like in that particular setting. So and in the general setting is the same. So you have a domain of discontinuity in one space, and what you do is that you define a thickening in possibly another space, and the domain of discontinuity is the complement of this thickening. So I didn't discuss precisely because it depends, like in the way that Guichard and Wiener they do, it depends from the target group G, the relation between the P and the Q. Is not that simple. Like it's more simple if you do it with balance ideal, but you need to introduce that whole combinatorial side. But you should just think that in general for all this group, like think classes of group that we have, like SP or SOPQ, like you always have a notion of isotropic subspaces. And so what you do is that you have a parabolic, and so you have a limit curve in certain flag space, in that setting isotropic flag spaces. And then what you want to do is that you remove a thickening of that curve. So isotropic subspaces of different dimension that contain points in the limit curve. But to tell you precisely, like it's just easier to do in some examples. Yeah, yeah, of course. Other question?
where it's large parallel. So that's some connected domain.
Exactly.
And you have constructed the full map.
Yes.
Is there a section, and topologically there is, but is there some section with any extra structures that you get something like a black bundle?
Yeah, we haven't discussed that. But what is nice is that, yeah, you have this diffeomorphism between all the points, and in fact, that's for tomorrow. It will be important when you want to study the fiber. This is like, yeah, work in progress of one of my students is really seeing, yeah, the way that we do it here is really using properties of this domain being PSL2R invariant, and or H invariant, where H is a rank 1 group. So I'm doing for PSL2R and surface group, but it works more generally for fundamental group of like manifold that are quotient of rank 1 spaces. Yeah, I don't think I ever really worked out the examples, but yes, you can take maybe some example there. And yeah, so our theorem, it just works generally when, yeah, I think I have it in the next slide. Instead of having pi 1 of S, is pi 1 of M, where M is a manifold, M is a quotient of a rank 1. Yeah, it's really using the main property that we are using is that omega has this H invariance, and the fact that is being rank 1 is hyperbolic, and we can use the barycentric construction. Basically, these are the summary. Other question? Yeah. So here is just a semi-simple Lie group. There will be restriction of not always you will have Anosov and Colin Davalo has a similar proof, maybe slightly different setting, but his proof is independent and using very different method. Is a very nice proof. But I will not address that today. And so, yeah, this is what I was saying is that our theorem is more general because instead of a surface group, you can look at uniform lattices in semi-simple Lie group of rank 1, and like what are representation, you are really embedding this rank 1 Lie group in your space. In fact, I think you can relax these and just ask finite kernel, but for today's, you should just think a surface group, PSL2R. And in fact, what we prove is that the domain of discontinuity, so the formation retract to a closed manifold that is a dimension of the difference between the dimension of the flag space where you are minus the dimension of this is the symmetric space associated to H. So this is H2 when H is PSL2R. Okay, so I think what I want to do is that I want to give you at least the main step of this proof, and if I can, the full proof of the main technical lemma. And so as I was saying, I think really the co-compactness is really crucial for our proof, because what we do is that we study the topology at Fuchsian point, and then use the fact that the topology is constant on the whole Anosov component. And in order to prove that this quotient is a bundle, we use, I think this is the main theorem that we prove. And so it's the fact that any manifold with the proper action of PSL2R, then you can always find a PSL2R equivariant fibration, locally trivial fibration. Exactly. Yes. Yeah. Exactly. Yeah. And the second theorem is about the structure group of those of this bundle. And as we were saying before, like these just work in general for rank one group, and again the second theorem as well. Question? So I have 10 minutes. So what I'll just maybe say 2 words about how using this theorem let you conclude is basically applying X and Y in one case, and then I'll mention ideas of the proof behind these, and if I have time, I go back to the domain of discontinuity. Okay, so once we have, so if you assume this theorem A or theorem A and B, if you want the structure group, then our theorem really comes, because what we do is that we have a uniform lattice, and from the fact that this is a uniform lattice, you get that our domain of discontinuity is preserved by PSL2R, because the limit map is, and we have that the PSL2R acts properly discontinuously on it. So this proper discontinuous action is slightly like you need to prove. Like here, I had a case where, in fact, you have a uniform lattice acting properly discontinuously on a manifold is equivalent to the full group PSL2R acting properly, and is really working through the definition of proper discontinuity and just seeing that it becomes a proper action of the full group. And so once you have that, so we have this manifold that is invariant under PSL2R, and where PSL2R acts properly discontinuously. And so we can apply lemma A and B, and we can have a fibration into the symmetric space of H2. And this fibration is smooth. That will be nice, because you can construct non-smooth projection that we will do tomorrow. And then the structure group is really the circle action. So they are like, we also have this circle action that again will come up tomorrow. And then this is the claim that I was making about whenever you have a uniform lattice and the manifold that has this like smooth action, then you have a proper discontinuous action of the lattice if and only if you have the full group acting properly. And once you have this, once you are in that context, then the first action is co-compact if and only if the second action is co-compact. And so, as I was saying, the main, so this is really the crucial point of our proof, and the main tool we use is this notion of barycentric for a measure, and this is where we really use the fact that the symmetric space associated to, well, in this case H2, is hyperbolic. So let me give you like the main idea. And yeah, it might be a little technical. We need to define a lot of maps, but yeah, please stop me if you get confused. So the first point is that we start, so we have this torsion-free uniform lattice in PSL2R, and so this lattice acts freely, properly, discontinuously, and co-compactly on X. And so, like, what's happening is that then the quotient is a closed manifold that, and the quotient of the domain of discontinuity of this manifold, the fundamental group of this manifold with the fundamental group of X is really gamma. And so you can really construct the homomorphism between those two fundamental groups. And since H2 is contractible, or the symmetric space is contractible, this map is induced by a map between the quotient. This map, like you cannot immediately assume to be smooth, but you can smooth it up. And so this is just using the density of smooth function. And so what you can do then is to lift this map to a map that I call little f, a smooth map from X into H2. That is H equivariant. This is not the map that we will use, but we will get there soon. So from this map F, what we define is another map. So for every point in X, we have this big F, big Fx, is a map from PSL2R in H2 that is defined in this concrete way. And so, and this map descends to a map into the quotient that we will keep, yeah, so here. So we'll keep, with abuse of notation, we'll keep denoting the map on the quotient effects. And so we will, we will need this map to then apply the barycentric construction. But let me give a side and define this barycentric of a measure. So this is something that you can do in general when you have a finite measure of compact support on H2. What you can do is that you can define this B, this map that map any point in H2 into the integral between the square of this distance integrated along this measure. And this is smooth, like strongly convex. This is, the square is important and proper, and the Hessian is a positive definite. So the point is that this map has a unique critical point, a global minimum, and so you define the barycenter of this measure to be exactly this unique critical point for this map. And so this notion of a barycenter is what we need and what we apply to this pullback of the Haar measure on the quotient. Push forward. Is like we have the Haar measure on PSL2R that descend the R measure here, and then we push forward using fx. And what we do is that we use this barycenter, and so these define a map from X into H2. And so this map F bar is now the map that give us the trivialization. And for that, like we are using like to prove that this map is PSL2R, like we then need to check. And so we need to check that this map is PSL2R equivariant, smooth. The smoothness is the more involved, just checking that at every step, all the things we are doing are smooth, basically. And it's a submersion, so it's a local trivialization, which is what we need. And so I think I have maybe 1 minute, but I think I'll stop here because I don't have time to do the other proof, but I'll be happy to discuss. And tomorrow we'll do 5 minutes.
Thank you, Sarah. Are there some questions? Maybe Subhojoy, yeah.
So capital X was always this PSL2R mod gamma, or what is
So
the...
X for us was a domain of discontinuity. Like, so this is, like I was discussing this general, this is, for this theorem is just a general X. So this last proof that I was giving is in this general setting where X is just a manifold with a proper action of PSL2R.
I see.
And, but the point is that in order to apply to our theorem, the X is the domain of discontinuity, the omega. And so omega, like you have the limit curve that is invariant under the group. And so then you have your domain of discontinuity invariant under gamma, but because gamma is a lattice.
The proof, I got lost.
Oh, yeah. The proof is...
it's PSL2R mod.
Yes, so like we use a lot X or X mod, is the PSL2R mod gamma. Like, sorry, I think, well, we start with an action of, so not this theorem, this theorem. So here we start, you start with this manifold that has this proper action of PSL2R, and then you move like here, like you just have a projection and you like it is not using anything.
Do you really need PSL2R, or is any rank 1 Lie group?
No, this proof is any rank 1.
Any
so
rank
I did it for PSL2R just for concreteness, and you just, whenever you see PSL2R, you replace by H, this rank 1 Lie group, and wherever you see H2, the symmetric space of that rank 1 Lie group, and it works.
Great, thanks. So the other thing is that, I mean, even in higher rank, because it's non-positively curved, you still have barycenters of measures, right?
Yes, but I think here you don't have the uniqueness.
Ah, okay.
Yeah, and there might, like, we didn't find the,
So are there more questions? Well, I mean, I wanted to know, I'm more familiar of this work by Kano, Navrete, and Siade about limit sets and domains of discontinuity for discrete subgroups in PSL-NC acting on CPn-1. There seems to be lots of echoes with what you're talking about.
I should look.
I don't know whether there's definite connections, whether that's even a special case of what you're doing.
I don't know this word, like I didn't recognize it. Like, yeah, I will look. I don't know.
Okay, maybe we can talk later.
Yeah, absolutely. Thank you. Yeah,
Okay.
that would be nice.
Okay, any further questions? No. Okay, let's thank Sarah again.
Thanks.